Okay, good day. This is my chosen topic, chapter on the book Essentials of Computational Chemistry, Theories and Models by Christopher Kramer. My chosen topic is chapter 6, Ab initio implementation of heart 3 molecular orbital theory. My name is Joseph del Rosario. In this lecture, we will focus on heart 3 not as we have seen it, but up till now, which is the empirical implementation, where approximations are made by in replacing certain kinds of uh, integrals, but instead we're going to look at the ab initio heart refract theory, meaning ab initio from the beginning. In particular, after a brief review, I'm going to focus on the pieces X and their use in ab initio calculations to construct a linear uh, combination of atomic orbitals type wave functions. Next slide. First, we have to know what is R3 Fact 4. This is used to solve electronic strategy equation. Uh, we could talk about that in general, electronic structure theory, but this electronic structure uh, equation we got from the invoking the from Oppenheimer approximation, and it basically says what all the electrons doing and what's the electronic wave function, which depends on all coordinates of all the electrons detail and parametrically all the coordinates of the nuclei, which in these approximations are temporarily frozen in space. We will get also an electronic energy out of that, and that energy does depend on where those nuclei uh, are, and that will map out the potential energy surface if we solve this for many different possible values of nuclear coordinates. These coordinates, this electronic wave function, uh, PSI, psi rather, is our target, psi target, as well as this electronic energy, because from psi we can compute all kinds of things. We can compute polarizability, dipole moment, things like that, and then we can get derivatives of psi. We can get more can more get elaborate properties from the potential energy surface if we evaluate this at the handful of geometries. We can try to keep tweaking at the geometry, maybe to minimize energy, can give us a equilibrium geometry and getting us the second derivative of the electronic energy with respect to nuclear coordinates will give us a vibrational frequency. So there are many things we can extract either directly from psi or from this energy or its derivative. So next background, let's talk about the R3 focus orbital theory. We will walk you to the Born Oppenheimer approximation to get the electronic equation that then you say we're going to use the single Slater determinant uh, that's going to it's going to be the wave function, and then invoke the variational theorem. These two are the uh, main contributors of this Hartree Fock molecular orbital theory, Douglas Hartree and VA Fock. Um, we can apply the variational method and say um, those orbitals are going to be the ones that minimize the energy, and turns out We're not going to prove this right now, but if turns out those assumption, the last couple assumption wind up being equivalent to the assuming of that electrons sees as just an average charge field to the other electrons, and that averaging is what introduces a little bit of error to this. Uh, Next slide. Okay, this is the in terms of review. We will focus the wave function. We will take you all the way back to the sort of foundational principles of quantum mechanics. They are all chunked here in a single slide, which I may shown before. But the fundamental postulates of quantum mechanics is that there is this thing called wave function, the symbol is psi. Uh, Buried inside the wave function is that all information about the system is necessary to derive any properties of system, and the way which may obtain those properties there is some operator which acting on the wave function will return to the observable, and when the wave function is an eigenfunction, in particular to this rather simple looking equation holds true. So the problem with the wave function, of course, is the conceptually a little bit big. This kind of difficult to read the graphs what's in the wave function as we've seen it fair amount of them. And now hopefully we will have to appreciate better that's anti-symmetrized product, which is the what we usually work, an anti-symmetrized product of some rather than complex three-dimensional functions. But in any case, if we just stick to the conceptual level, I like to tell uh, the listeners that wave function is an oracle, right? If you question by probing it with an operator and gives and it gives you answers which uh, tell you now that what's the observable properties you would expect based on the operator, and and in fact where do we get these wave functions? Well, as theoreticians or computational chemists, we refine them. And the process of refinement is a variation process. And that is, we are armed with a variational principle. Says that when we apply the Hamiltonian operator to any wave function, Hamiltonian operator, uh, function, we will never get an energy out of that is lower than the correct energy associated with the exact wave function. We don't we often don't know the so our goal tends to be the to try rationally to improve the wave function, and we judge whether we have improved it by using different mathematical functions to construct it. It's a judge to that energy, if so energy goes down, energy goes down, uh, must be approaching truth. So that's why I have to have convergence of energy leads to truth that there is this question, if I can converge that test your oracle with the question to which we already know the answer, right answer, to where semi-empirical regime, for instance, where we're not actually gonna try making more complex, expensive wave functions. So next slide. Uh, this slide is an example of electron wave function that is the exact solution to the one electron Schrödinger equation for a single atom, and one of those solutions is the 2p orbital. The 2p orbital, and so this is the just illustrates the uh, mathematical functions if I express in Cartesian coordinates for a given uh, nuclear charge z, nuclear charge z, and then uh, the charge c here properly normalized atomic orbital wave function that follows out exactly from the solution of the Schrödinger equation, however you pronounce it. And I show this because of to the extent that we're gonna need we're gonna need to use the mathematical functions uh, e- even in more complex systems like molecules in with many electrons. Certainly, it's kind of reasonable questions that functions will be useful in terms of being efficient to build more molecular wave function will the atomic orbital wave function there get out what they've got right shape for atom, and then hopefully we have a good approximation to the shapes of the to the shapes that will we need to put together to describe the electron density in molecules. Next slide. Uh, and I emphasize here, although it's a reasonable assumption to say that atomic orbitals could be useful basis functions. It's by no means our only goal is to come up with a set of functions that can describe the varying amplitude of electrons. Electron density in space, no one could do so many different ways. So we will talk about atomic orbitals till now. So the CH bond here, the CH bond uh, might be derived from some linear combination of the carbon s orbital and a carbon p orbital and a hydrogen uh, s orbital, and maybe an electro hydrogen p orbital. Not because hydrogen is using a p orbital in sort of formal sense, like some excited state hydrogen is. It's just a function that it helps to polarize spherical density towards the carbon atom. So some small uh, admixture of this might be valuable, but an alternative would be simpler to sum together the orbitals along the axis of CH band, and if I add together all of this densities, it looks like this kind of sigma bond would look. It's just to emphasize the functions, or a function is just a math, or by a certain point of chemists who really like atomic orbitals. But if you're a straight mathematician, it would be no clear there will be no clear reason to why would you give one set of basis function any more precedent than another. Next slide. Here our goal in the variation process then it's that we indeed going to take this molecular orbital functions, wave functions, which are expressed as a linear combination of basis function. Uh, we will evaluate the energy by looking at the expectation value of the Hamiltonian, and just in case they're not normalized with it, we will divide the overlap integral here uh, of the individual molecular orbital s. And we've already discussed the semi-empirical theory that in order to maximize this energy, which is our goal, we want to solve secular determinants equation. We will extract roots e uh, that cause this determinant to be equal to zero, and for every one of those roots e, we will get a unique set of coefficients that multiply all our basis function and describe a different molecular orbital. So, and the integrals themselves are buried uh, in that Hij here, Hij here, uh, orbital H orbital, so orbital H integrated overall space included kinetic energy integrals, one electron nuclear attraction integrals to all the various nuclei, and finally the repulsion of all electrons with other electrons, all the other electrons, and it's slightly sloppily written, and this just gives us the idea on when there are many electrons, you need to include their mutual repulsion with one another, and it's that in the last term it's a little bit tricky that the Hartree-Fock approach gets this term by saying we will not interact instantaneously one electron with another by rather every electron in molecular orbital, we will see the average of the other electrons in their own orbitals. That's the Hartree-Fock approximation. So approximation when it's many electron wave function, we will build that many electron wave function in which we will know the needs to be anti-symmetric and anti-symmetrized product of one electron molecular orbitals. We can call a Slater determinant. So then the whole determina approach can be sort of chunk in one density matrix slide again into a Hartree-Fock procedure, and we've looked at this slide. Previously, there's a detrimental equation which roots e are extracted every one of those roots e. So different molecular orbitals that we have this term in the Hartree-Fock matrix that involves the density of matrix, the density matrix which tells us the um, degree to which individual basis functions the lambda here, uh, the lambda, uh, the lambda, and sigma are contributing to occupy molecular orbitals, and the degree to which these electron repulsions, mm, which are computed for all possible basis set interactions, contribute to the actual molecule, because of the if the basis functions are not really used in any of the orbitals, then uh, not know how electrons occupying those basis functions would interact with one another. So again, that was sort of refresher, and I know that we would we went too much in the review portion. We do this of various integrals. We need to evaluate in semi-empirical theory. uh, we had series of approximation ranging from very extreme, like the complete neglect of differential overlap, which gets almost all of these two electron integrals, and we have neglected the diatomic uh, differentials overlap, which save so many of them, but I don't want to focus any of these kinds of approximations. Uh, Next slide. So what functions to use? Uh, we focus on basis sets being derived from solutions to the one electron Schrödinger equation for a single atom where we get atomic orbitals. We've really been talking about the sort of Slater type orbitals, the STO. Slater type of orbital, STO. There is another name for this. That is orbitals which one s orbital, for example, decays to as e uh, to the should be a minus sign here, e minus sign here to the minus zeta, and then this is the normalization for the line to this exponential decay that is linear in R in the exponent, and then characteristic of an actual atomic systems, the electron density decays exponentially. Exponentially. However, if you were to take a Slater type orbitals, in which e to the minus zeta dependence, and place them in the generic for index integral, and the intent that would be the new the last sigma could be the basis function, that even though they are Slater type orbitals, in each one might be on different atoms. So mu would be the one in position to space in space with nu uh, would be at another position in space. A lambda, yet another sigma, uh, yet a fourth, and the problem is there's no analytical way to solve this integral. In that case, no one has ever figured out the way to write down the sort of function in the exponents, the nuclear positions that would give the value of the integral. Now we can solve the numerically in uh, there are codes that we have actually developed extremely efficient quadrature approach. That's usually how you would solve integral numerical, but it was not convenient when people were first thinking about this uh, problem solving. Which is theoretical chemists made a suggestion that instead of using STO, which decays exponentially, which are why not use Gaussian uh, type function? So here I've got 1s, put 1s in quotes because it's no longer 1s in the sense of it's an exact solution to the one Schrödinger equation instead of approximation that solution, but the difference is that it's now decays exponentially with r here, uh, squared, not r squared, but with r So that means it's gonna die of little bit too quickly with R. That is normalization factor. That's approximation for Gaussian in three dimensions, and I've changed the name of the exponent to zeta to alpha here. Sort of to keep things distinct, but there's a graphical picture of what that looks like. If blue is the one S Slater function, you see this exponential decay. The red line is the Gaussian function. Uh, red one is the Gaussian function. Uh, Decays more quickly. It begins more slowly when r is less than 1r squared, smaller than r. Then uh, at 1, it is exactly equal r squared to r, and then after 1 starts decaying a little bit too quickly. Notice another difference between the two. It's a Slater type function. Now, it's cusp of the nuclear position, right? It is non-differentiable. Well, if I were to go in a direction that there'd be a sharp point, but the Gaussian is nice and smooth and differentiable at all nuclear positions. So that's behave that's inconsistent with actual solutions to the electron Schrodinger equation. Next slide. Approximating Slater functions with Gaussians. We can do here. We can do better and better. If instead of using only one Gaussian or the single Gaussian to represent Slater function, we treat the Slater function itself like a molecular orbital. It's constructed out of atomic orbital basis function. We can actually treat the individual basis functions as things that are constructed out of the linear combination of other mathematical function. So in other words, this is the single basis function. We're going to build it out of multiple functions, and particular, I'm going to use the Gaussians to show here the sum of this Gaussians. There is this blue curve here, and it is almost looks like a line. It's because there is very small value of alpha, so it decays very slowly. And there, this green curve, uh, with a somewhat bigger value of alpha in the Gaussian, so it decays more rapidly. Finally, there's a red curve here. So you see, dies of relatively quickly, so it has the biggest exponent alpha. And if I need to add together the red, the green, and blue curves, I'll get the purple curve here. Uh, Purple curve is the label as 3G because it is a Slater type orbital approximated by the sum of three Gaussians. So these three Gaussians, kaya 3G, to this curve, the STO3G is the sum of all these three curves, the red, the green, and the blue, so that we will see it's the matching of Slater function much more closely that we have shown you in the last slide. Only one, we only had a single function that of which single Gaussian attempting to sort reproduces later here will actually go backwards and look at that. So much there were big gaps in this function in terms of its ability to match red and blue if you look at the contracted basis function. Purple really it's really quite early, so we start to get a very good agreement as we go further and further in its pretty good approach of combining so-called primitive Gaussians. We are optimizing these values of A that are multiplying the individual primitives in order to construct a so-called contracted basis function to its single basis function, but is contracted at the sum primitive Gaussians. So if you want to really be clear on the difference between the linear combination of atomic orbitals and a contracted basis function, mm, so the difference is the LCAO expansion. We will solve the Hartree-Fock procedure in order to find the best coefficients that I'm going to use to build my A results. But in contracted basis functions, this set in stone in STO3G refers to a table in a paper somewhere that says if you want to build the functions the best, you can make it look like 1s for us to for use in molecular calculations. Use these coefficients; they're not allowed to vary. To vary their, it just gives you this shape. That's the shape you'll use now. You do actually the actual computation of going to expand into these things because you're doing the integrals over this function because they appear this in this function. So contracted basis set. There's just another picture of STO3G approach. So the green is the sum of red and blue and yellow. In general, John Popol here optimize A and alpha values. Mm, was very active in semi-empirical molecular orbital theory. We will, while Dewar and Stewart and others decided to keep exploring, that Popol made a jump to AB initio theory, ab initio theory, and began optimizing basis sets. Initio Hartree for calculation in particular, he looked at a number of STO number G here. So you don't have to just add together all three. Presumably, if we added together four, we do even better, and six, but R still there is 10. I could have a fabulous function with STO 10G, STO 10G instead of just 3G. Now, we have to remember that as we increase this number n, uh, get more and more these functions that are going to appear in every single integral. So I'm going to have a whole bunch of integrals over primitives, and I'm going to compute the integrals, and I might want to keep that down. But because in any practical ones, the people used to, for a little while, uh, will use STO3G, so enjoyed the STO6G. Some popularity of these basis sets are called minimal basis sets because it tends to be used as there would be a single STO, let's say 3 for the moment, STO3G function as a single one of these functions for every core and valence orbital that an atom would be expected to use in molecular bonding for a hydrogen there would be a single one of these basis functions corresponding to 1s orbital. For a carbon, and there would be a single 1s, single 2s, then 3p's, that is a single 2px, single 2py, single 2bz, so that it will be total five functions: 1s, 2s, 2px, 2p, y2pz, and so on. You could just go through the periodic table and you would optimize these values of E to best reproduce the shapes of those functions. So what the here the interesting question, do you think of the hydrogen fluoride compared to the hydrogen bonding at the different, it's a very hydrogen fluoride compared to mercury hydrogen bonding is very different. And the fluoride, fluorine being much more electronegative, pulls density away from the hydrogen atom. Whereas in molecular hydrogen, of course, the density, while it is in between of the two atoms of sort of average, since it's closer, it's just focus on each. Is this the difference of reference age, and this age gets to keep a lot more of density. So I, I think what representing that is a molecular orbital corresponding to the sigma bond, uh, some sort of to be able to use this function each that decays more slowly. So that we will to describe amplitude over here close to the f, and its own functions to the point that it looks like an H plus, and this looks like a bit more H dot in some sense that to add flexibility, maybe what I have to do is in my basis set of let hydrogen have more than one s orbital. Uh, Stop calling these orbitals their function that means to be spherically symmetric. The way that 1s orbital is spherically symmetric, but tight function and loose function. The loose function, it's after a variational process and decide what are the coefficients those functions will be multiplied in any given molecular orbital, so that philosophically is referred to a multiple zeta basis set where multiple could be double, triple, quadruple. It's an indication every nominal orbital that is a 1s, 2s, or 3D. What you many functions will I provide to the that are meant to represent this orbital. Some looser, some tighter. Next slide. So the double zeta would be a single loose and single tight function, and clearly that's more mathematically flexible. And here is a picture of triple zeta: one loose, one medium, one tight. Triple zeta, in a sense that doesn't look any different than pictures. I've shown already three curves that, but a point when there were primitive functions, they were multiplied together in a specific with specific coefficients to build a single shape. Now I'm going to do is I'm not we will not specify the coefficients ahead of time, but what we're going to do is these curves to be its own basis function, and the coefficients of those MOs, molecular orbitals will be optimized by the variational process. Often people will make this approximation, uh, or I shouldn't say approximation. I guess they'll take this approximation step. Uh, Valence functions, but recognition in some sense that bonding which gives this to the variation. Mm. So sometimes a bond will be stretched in one direction, and sometimes it's stretched in a different direction that involves valence orbitals primarily core orbitals, in the other hand, so a 1s orbital in carbon, for example, those typically are not very much influenced by substituents and a result of computational efficiency. Mm, Maybe we really do only want to have one function, and that's going to be used to build core orbitals. The decontation, uh, we will go to the designing which functions we're going to have in this double and triple. So um, on splits zeta, on split zeta basis sets, but valence will have one trivial approach of course, we would be the fact so to take 1s orbital on hydrogen, 1s orbital on hydrogen, and STO3G. STO3G, if I go look the the 3G paper, you'll see the sub i's here. Uh, Fixed values in certain values of alpha that we will be in the table. In the table, there will be three values of one associated with an alpha and an A, two associated with an alpha and two, and those we will just give it the shapes. And what I'll do is I'll keep one alpha and two, one to keep the alpha one, two, and three values that were optimized uh, in other writings. But now we will just let these three A's float. It becomes three basis functions instead of just one. Correct. That is correct. Contracted from these three primitives, now Popol uh, actually did something a bit more sophisticated, that uh, he optimized the basis sets, that so-called the split valence, and they tend to these teams, you will see this competition in competitional papers. There's a number of AA series and number in a AE and G. In what this implies that G actually the David Gaussian basis set. So the number before there is an indication how many primitives are there in all the functions. So there is only one number, because there is only one basis function for every core orbital, and this in this particular basis set, those 21G 21G will be like the STO3G basis function shown here, and will be a contracted basis function formed for three primitives. Doesn't have to be there. It could be six, or for instance, there's a basis that's called 6 to 1, 6 to 1, and that's telling you the difference is the core is described with a little bit flexibility. I shouldn't just say flexible. It's not flexible, but it's a better shape because it has a better shape because if we build out six function out of three, now the thing is that are valence functions. So if you count how many numbers there are, uh, that tells you the split level of this basis set. So our only numbers here, that means there is a double zeta basis set. So there's an example of this where uh, to be carbon, that would say for the second quantum level, which is the 2s orbital and the 2p orbital. Uh, each one of those four different orbitals, 2s, 2s, 2x, 2px, and 2py. 2pz will have a a basis function, which all the 2 tells you that it will be formed a set of linear combination of two primitives uh, that have a loose basis function, and that one tells you that functions mm, it's just out there on its own, so it's not contracted out primitives, and it's just a function. So two tight primitives to make one basis function, one loose function, which is constructed primitives. How many basis functions are there in ammonium molecule using 321G? So we will do a quick example here. It's like counting up basis function. Counting basis functions, how it is in a useful exercise because the time spent calculation is dictated to some extent that how many basis functions are there. Then remember that number of basis functions gives you the dimension of secular determinant that you need to solve the total number of electron and integrals. One molecular orbitals in is n to the fourth power uh, because there were capital N basis functions. There's an S many molecular orbitals as there are basis functions. So n to the fourth as to n gets big, you will start to evaluate a lot of integrals. Notice incidentally that if one of those basis functions are adding up to itself, a sum of contracted basis functions uh, uh, will then that integral just go multiplied by all the sub-integrals. I'm going to have to add together these integrals because I expanded my function as a sum of other functions. In that case, we will actually look at basis functions. So let's start with an easy one. This is ammonia. Let's look at the hydrogen atom. Mm, there are three of these atoms. What kind of atomic orbitals are there? Hydrogen up to valence will actually that's all there in no core orbitals. So there's one S valence orbital. That's degeneracy of one S orbital. Well, there's only one of them. How many basis function will be involved when I look up for the valence? This is a valence orbital, and the valence orbitals are represented by one or two basis functions. So there are two basis functions that are brought to the topic. Here, how many primitives functions are there? In that basis function, uh, hydrogen we will be tight. There will be a tight one plus two primitives and a loose a primitive to two plus. So three, what is the total number of basis functions? There is one atoms of the number of basis function, uh, generally one. Uh, Three atoms, the number of basis functions, 3 times 2 equals 6. 3 times 2 equals 6 total basis functions. Uh, so that's a total of primitives. That's again the number of atoms uh, times the total number of atoms times the total number of primitives. Uh, that's 3 times 3 equals 9. Here, number of the primitives. We will have 9 total primitives here. That's to nitrogen. How many atoms are there? There's just one nitrogen. Uh, in ammonia, what kind of orbitals does it have? It has one s, uh, one s core and two s valence, and the two p valence. The genera C is one, one, and three. Uh, 113 uh, SS orbitals and P, the number of basis function. Uh, a core orbitally has one basis function. So the valence orbitals are to each. Uh, how many primitives are there? The core orbitals has three primitives. Again, for nitrogen, it, this is 3 to 1g, and each of the valence orbital is 2 plus 1, so the answer is actually 3 for every single one of the three cases. And now finally, when I add up this function, I'll find 1 times 1, there's a single 1s nitrogen there, and 2s on nitrogen, and there are two p's. It's double for each 3px, py, pz orbitals, and the primitives meanwhile are 3, 3, and 9. So if I sum all of this together, I discover 3 to 1 G calculation, hard 3 fact 3 to calculation of ammonium would have 15 uh, the 15 basis function to the secular determinant. So there would be 15, and I'll be solving for 15 molecular orbitals. That it would be 24 primitives. I don't know if I can remove my picture. There are 24 primitives, so the total number of two electrons integrals I would end up solving would be 24 times 24. 4 times 24, they're going to appear in some point in an electron repulsion integral. So 24 to the fourth power total integrals is a big number. So the polarization for functions. Um, Now the basic sets go that include other things. So here is the basis that Popol will design 631G. That is different from 321G in that core orbitals are now contracted to six primitives. Six primitives. And the tight function is not contracted to form 2, but it's contracted from 3. So it's got a little more detail in its shape. And finally, the loose function continues to be just a single loose one. But here you see something new, and this is some kind of older notation. Um, star, or the asterisk. Originally, when Popol did this, uh, this kind of did the first time, the first star you would tell it tells you to add so-called polarization function. The first, the first function is, is add function on heavy atom, and by heavy here, electromos of the first and second row atoms because that is the original work was done, and the D functions are sixfold degenerate, and if that seems a little curious because you seem to see that there are only five d orbitals. Key point as a key point to this function here. So if I tell you write down the d functions in Cartesian coordinates, there are six of them. If you take a linear combinations of them, you can show that you make five canonical d functions, which, if you can remember, your quantum mechanics, they are usually not indexed by Cartesian coordinates. They are d minus 2, 2 and d minus 1, and the 2d and d0, d1, and the d2. So you can represent those five, but if you can make an s orbital, so think um, it's like a dx squared plus y squared plus z squared. If you remember x squared plus y squared plus z squared, that looks like a sphere, so it looks s orbital. It's an extra orbital that comes working in the Cartesian coordinates. So slide. So for each f, here's an interesting observation. If you do the Hartree-Fock calculation, so this is no longer a hydrogen fluoride. This is Hartree-Fock. Hartree-Fock. Uh, just look how to do on ammonia, but we're going to use to 1G. We're gonna use 631G, 631G, going to use an infinite basis sets of S and P basis function. Now in practice, of course, nobody did infinite. What they did you now is 10, 20, 50. Now in practice of course, nobody did infinite. What they did, no, this is I've said the 10, 20, 50, 100. So lots of S and P basis functions on nitrogen and S functions on hydrogen. When you do that calculation, you predict, if you do a geometry optimization, that ammonia is planar, and we know ammonia is not planar. Ammonia is not planar. So if you see, you give it five exclamation points. So that's quite a bit of shock, that part of the issue, that in the absence of polarization functions, you can just describe the electron density quite as accurately as you'd like to give just to give you a feel that what a polarization function does. Here is a molecular orbital of water, and I actually discussed the orbital in atoms, and you're now looking at sure the black overlaps uh, and white overlaps. The white, but if I were to add a little bit of character of this uh, D function, now we continue basis. The D function of this, not saying the oxygen has occupied D orbitals or anything, it's a mathematical function. I'm going to use to try to improve my description here. Uh, the electron density is space. Uh, if you look at this white overlapping plane, uh, p orbital. Uh, It's gonna increase the, it should kind of down in this lower region, but there is this black part overlapping with white. Uh, well, that's the that will destroy the amplitude of this region. So it has the effect of bending, polarizing the p orbital of oxygen towards the two hydrogen uh, atoms, and of course that gives us the better overlap. And this now looks like more like a sort of sigma bonds that it does over here, and that's the utility of this polarization function that we've now gotten to a stage uh, where we use these atoms all over the periodic table. And you might want to more of this one set of polarization function, which if one is a set is a good, maybe a loose set, and set A at tight set is even better. So the more rigorous way to describe the basis of a function set tends to um, be not with the stars, uh, and one should try to avoid saying something like 631 G star, but instead just specify 631 G 3D or 2F comma 2P, so that it means that all the heavier atoms I'm gonna put in 3D polarization functions and 2F polarization functions. So if D is good, F only improves my flexibility, and then after the comma is how many polarization functions and what kind of hydrogen atoms, technically on helium 2, but it's pretty rare. You do an interesting calculation on helium atom. Now this is the basis set we wrote here is perfectly the decent notation, a little bit unbalanced. Now we mean now when we balance it, it's now it's been observed however many years essentially, but every time you split contraction, the valence and the valence are you from uh, the valence you go from zeta to triple zeta to quadruple zeta, you will get about as much improvement in energy by adding polarization functions in the double zeta calculations. So the Dunning basis set, uh, we will see here in the literature that sort of naming convention here, the Dunning basis sets are relatively popular because they're usually named as CC something here and CC here, correlation consistent. Uh, like we've shown the case of P, V and Z is a number or it's a number or letter, and it's an acronym. It's an acronym which stands for correlation consistent. That means the Dunning optimize and his contraction, the uh, contraction coefficient in his exponent for correlate calculations as well as Hartree-Fock calculations polarize means they are polarization functions. They follow the scheme. So that I just sort alluded to, namely every time you track, you add a new higher angular momentum function, and you split all the lower ones and further, and then n is either D for the double and V is valent. Uh, so this is the valence double zeta. If the D valence triple zeta, It's a quadruple, and if you go past the, you just start using numbers instead of saying quadruple or quintuple, sextuple. So you will see those basis sets in the literature. Diffuse functions here of what will really lose bound electrons, and what when does that happen will maybe we will have an anion, so extra electrons, and they're usually not held all tightly, maybe computing the excited state, and we've been taking something out of the bonding orbital, and I've put it presumably a bonding orbital, or uh, loosely held orbital uh, to orbital Rydberg states. Actually, excitation Z, they are so high in energies, typically with the electron almost sits underneath in its positively charged state, and that is absorbing around it looks like an atom so far away from all of this that is involved, loose electrons, so that calculation on those kinds of states or species that we know is, if you don't have the functions that puts a density far away from the molecules. Of course, you cannot predict an orbital, but uh, that is out there, that is there far away from the molecule. You can only predict that you provide basis functions to set amplitude in space, and so-called the augmentation functions, augmented functions, or diffuse functions are indicated in Dunning basis sets by AAG, or augment or in Popol basis sets. And this is if there's a plus here, means that there are diffuse functions on the heavy atoms, and usually valence space. So let's say it's a carbon, it will have extra S and extra Px, Py, Pz, and the include is that exponent on. Those function will be quite a bit smaller, and that the valence exponent that is those functions are decaying very slowly, so that they have reasonable amplitude quite far away from the AB. If you see those classes, 631, 631 plus plus G, that amplifies uh, these two positive notations. Amplifies that implies there's a diffuse function in each one of the hydrogen atoms. So I usually tell that I think hydrogen, there is a hydrogen heavy atom, maybe it's an angstrom away. If you got a diffuse function on the heavy atoms, you've already got a function that barely decayed on time. Yeah, you get an angstrom away. If I now put a fuse function on hydrogen, it's kind of hard to tell that function from the one that was already on the heavy atom. So about the only time it's really useful to a diffuse function on hydrogens. If you're going to generate a hydride somewhere along, say, reaction coordinate, it's the case you've got a hydrogen, and that's almost all by itself. It needs to accommodate a negative charge. So sure, there's a good reason to have a diffuse function. Otherwise, hmm, We will think that it's usually just a waste of time to introduce instability from having uh, functions that are hard to distinguish from one another. You're actually doing the SCF equations, but in any case, that's notation means so that's all you really need to remember that these exponents added functions with exponents such that they decay slowly, and as a result, you'll be able to accommodate things like an ion, and the general rule tends to be if you don't include those functions, you really tend to do okay for the molecular geometries. But you do badly for the energies because you're basically forcing an electron, at least one electron, to be much closer to the rest of the molecules that would otherwise be to be, and why are you forcing that? Well, because you didn't give any basis function that let it get away, so you can for instance, you can do calculations on systems that can be that can be made experimentally. So there are some molecules that will not bind an electron, at least not definitely. These things called resonances uh, might not just stick. It's very briefly. Many systems are now known to have negative electrons affinities they will spontaneously detach an electron in its temporarily. Uh, but if you can do the calculations, those the we tend to use these basis sets that are centered on the molecules, and we say an electron leaves where it becomes free electron. But though you remember those quantum mechanics, the wave function for this free electron is just a sine or a wave or a cosine. It's a standing wave that we don't have any of those in our basis set. So how that poor electron get away. So I bring this point or bring this point so hopefully not to be confusing but to emphasize that the electrons have to go where this function let them go, and they can go anywhere else. So thinking about the basis sets, it is important because you need to pick basis sets that's appropriate to a problem at hand. So thank you for listening. That is my presentation for chapter 6 of Hartree Fact ab initio calculation. Thank you.